All right, we're talking about the second derivative and how it affects concavity. This is Mr. Smith from Advanced Math Tutors. Awesome. All right, well, before, in the first derivative test, we found out how to tell if a function was increasing or decreasing. Now, the reason we need the second derivative to help us with graphing is because a function can be increasing in several ways. It could be increasing along these lines. It could be increasing something like that, and those are different shapes, both going up though, okay? Or it could be increasing in a straight line. Now, straight lines are usually pretty easy to determine here. I mean, hopefully by now you know what a linear function looks like. Okay, and decreasing, we have the same problem. A function can be decreasing this way. It could be decreasing like this, or it could be, again, a straight line. Now, these two cases over here, we'll box these guys off. These guys, they're not really that, they don't pop up that often because most functions don't increase and decrease linearly, unless it's like a piecewise function or something weird. So for now, I'm just going to disregard those guys. Maybe we'll take a look at a linear function later and see how all this ties in. But here is what we got going on. A function that looks like one of these two things is called concave down. And I'm going to explain why in a second. Concave down. That's these. Let me move these guys over some here. Yo, chill. There we go. A function that looks like one of these two guys is called concave up. Okay, and you can kind of put them together. Check this magic out. Let me get rid of this. We put him here. Put him here, and they make a bowl. Look at that, beautiful. Opening upward. Okay, that's how you can remember concave up. If it makes part of a bowl or all of a bowl of opening upward, that's called concave up. If, let's move these guys, it makes a bowl opening downward, well, we can just call that concave down. Cool. So this function here is first increasing on this part and then decreasing. So the first derivative is changing. That's first derivative tells you increasing and decreasing. However, it's concave down the entire time. That's going to come into working with the second derivative. Okay. Now, I want you to notice something here. Even though the slope is positive and then negative, the entire time on this interval, what's happening is the slope is starting out at some positive number, right? You can see that its function's increasing. So it's positive over here. Then it just keeps, it's still positive, 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 but you can see it's getting smaller because it's going to be 0 at the very tippy top of this curve. So it goes from positive to 0 to a negative number. That's more negative. Okay. Essentially, what's happening here is the slope is decreasing. The slope is going from positive to 0 to negative. That's not a sin. That is what is happening. That's exactly what's happening. Now, if the slope is decreasing, let's check this out here. Ready for this? This is the magic. The slope is just f prime of x, right? That's how we find slope of a function. The slope at the tangent line, the slope at any point is f prime of x. If that is decreasing, if f prime of x is decreasing, well, we know what's happening. If f prime is just some function, we write it f prime because it relates back to the original f, but it's also its own function, you know? Just like, you know, you're related to your parents, but you're your own person, you know? You're totally badass, you're cool. So, oh, I can't say that. I take it back. You're bad butt. So f prime of x decreasing means that we can derive this function here. Check this out. We can derive f prime of x to get f double prime of x. But f double prime is really just the derivative of f prime. And the derivative of a function tells you increasing and decreasing by its sign. So this may seem a little complicated for right now, but f prime is decreasing if f double prime of x is less than 0. And that's how we tell concavity. Okay, let's write this f of x up here. F of x is concave down. Every single one of these three things here is the same exact thing. Let me move this up some, get this out of the way. There we go. Let's move him over. F of x concave down, f prime of x decreasing, and f double prime of x less than 0, negative, all mean the same exact thing for f of x. So if you're told f prime is decreasing, that means the slope is getting smaller and smaller and smaller. So here, again, this is just a picture of this, positive to 0 to negative. Now it doesn't have to be this whole piece. It could just be like part of it. Like this guy might not be there. Now it's just going from 0 to negative, the slope is. So that's concave down. Over here, let's move these guys up. You can see the slope is going from a negative slope right here on this side, negative, to a 0 slope to a positive slope. So essentially, f prime isn't decreasing in this case, it's increasing. And if f prime is increasing, then f double prime must be positive, because a function is increasing if its derivative is positive, and f double prime is the derivative of f prime. And f of x is going to be concave up when this happens. If the slope of a function is increasing, that's the derivative is increasing, then the function is concave up. And that's how we use the second derivative. We simply take a function, derive it twice, and the same way we found out where the first derivative was positive or negative, we're going to find out where the second derivative is positive or negative. But in this case, it doesn't mean increasing and decreasing when it's a second derivative. It means concave up and concave down. So these are the big relationships that you need to remember here. I'm going to say it again just to go through. These are very, very important. F of x is concave down means f prime is decreasing, and that means f double prime is less than 0. Now this last one right here is the easiest one to check. It's easiest to tell where a function's negative. So when you're asked to find where f of x is concave down, you don't start looking for that right away. It's difficult to answer. You find where f double prime is negative. That's much easier to answer. Same thing with concave up. Now, functions are not always concave down and concave up, like just by themselves. Sometimes they change. For example, let's look at a curve that looks like this. All right, now, this function's always increasing, so the derivative is always positive, but the concavity is changing. You can see originally the slope is positive and it's becoming less positive on this little part here, okay? So slope is very, very steep, and then it's kind of flattening out a little. It doesn't flatten out all the way, but it flattens out some. But you can also tell that that's a bowl opening downward, just that part. That's a bowl opening downward, okay? Concave down. On the part up here, we'll use yellow. Right here, well, that's a bowl opening upward. That's concave up. Well, if it goes from concave down to concave up, then it must, at some point, change concavity. Now that point has a very special name. Right here, you can see this. That's called an inflection point. Okay? That's just a name for where a function changes concavity. Sometimes they call it a point of inflection. That means the same exact thing. It just depends on how you're feeling at the moment. Point of inflection. There we go. Man, oh man. There we are. Same exact thing. And all that is a point where a function we'll call f of x changes concavity. Okay? And we know concavity changes if the second derivative changes. So that's how we find points of inflection. A point where the sign of the second derivative of our function, f double prime of x, changes. So if f double prime goes from positive to negative, that's an inflection point, as long as there's a point there. If f double prime goes from negative to positive, that is an inflection point. So let's take a look at a function here. Let me find a nice function. I got some papers here. No. Where are we at here? Let's just do this one here. Y is equal to x cubed minus 12x squared. All right. Now eventually we'll be able to graph this entire thing. We've actually got all the pieces that we need together here. But let's say we're just looking for inflection points and concave up and concave down. Okay, so the question is going to be, here's the function. Find all points of inflection. So we want all the points of inflection, POI. They are points. We want to know where is the function concave up. I just write CU for that because I'm lazy. And we want to know where is that function concave down. Well, these three things are all determined by the second derivative. So we got to do a little bit of calculus here. First we find the first derivative. Well, that's easy. 3x squared minus 24x. Now we need the second derivative. No problem. Y double prime is 6x minus 24. Okay? First derivative finds where a function's increasing and decreasing. Second derivative finds where a function's concave up and concave down. And it's actually very, very similar to finding the maximums and minimums. We're going to first find out where the second derivative is undefined. In this case, 6x minus 24 is never undefined. And we're also going to find out where it equals 0. So it's similar to finding critical numbers, but these are not called critical numbers. So when we solve this, we're going to get x equals 4. And what we're going to do is the same exact thing we did with the first derivative. We're going to make a number line with all these points. Again, they're not critical numbers, but essentially, like, you could think of them as critical numbers for the second derivative. They don't call them critical numbers. I don't know if they call them anything, to be honest with you. If it ends up being a point of inflection, then that's what they call it. But it doesn't have to be a point of inflection. Remember, the second derivative has to change sign there. Okay, so 4 could be a point of inflection. We're going to do some math and find out. If x is less than 4, I want to know, what does y double prime do? Is it positive or is it negative? So I'm going to plug in a test point down here somewhere, like, it doesn't matter, 0. I'm going to plug 0 into the second derivative to see if it's positive or negative. When I plug in 0, I get negative 24. That means the second derivative is negative, and if it's negative, that means the function is concave down. When I plug in something greater than 4, I don't know, like 100 kabillion, whatever, blah, blah, blah. Okay, it doesn't matter. Any point bigger than 4, you plug it in, you're going to get 600 kabillion minus 24. That's a positive number. The second derivative is positive, meaning this function's concave up. So 4, when x equals 4, remember these are x values, the function changes concavity. So there's a point of inflection there. That's when x is 4, and when x is 4, we can plug 4 into here. We get 4 cubed, which is 64, minus 12 times 16. What is that? 12 times, well, 16 times 10 is 160, and 32 is 192. So it's 64 minus 192, 192, and that's going to be what? 128, negative 128. There we are. That's our point of inflection. It changes concavity from concave down to concave up. So it's concave down from negative infinity, because this arrow goes back forever, all the way up until 4. And we don't include 4 because it's not concave down at 4. It's changing concavity there. And we write the concave up interval as 4 to infinity. That's this whole number line part here, 4 to infinity. There you go. That's what the second derivative tells us. Now, if we were going to graph this thing, it would look along the lines, hopefully you know what a cubic looks like. It would look along the lines of this guy. It's going to go, let's take a look at the equation again, x cubed minus 12x squared. We can find the zeros real quick just by factoring it. X minus 12, so it's 0, we go to 0, and to 12. There's a 0, so that's 12. And 0 is a double root because it's x squared, so it's going to look something like this. I don't know exactly how far we're going to go down right yet because we didn't find the minimums. And we said there's a point of inflection at 4, negative 128. So it goes down pretty far. But that's going to be like right here, we'll say. 4. That's the point. And you can see that the concavity is changing. On this side, there's a bowl opening downward, concave down, which is what our interval told us, negative infinity to 4. And on this side, there's a bowl opening upward, concave up. Inflection points also are points where, hopefully you learned somewhere along the line, that a tangent line is a line that touches the function just at one point. That's terrible. So a tangent line could be, oh my god. Let's do this. There's a tangent line like that. Okay? Just passes it and it's always above it there. But at a point of inflection, what happens is the tangent line actually goes through the function. Like that, you can see. So that's also how you can tell if it's a point of inflection. The tangent line will go through the function. And that's really all you need to know about those things. For right now, we're going to do some graphing later on, and we'll put all this stuff together.